Why do we need concrete protective liners? Concrete is a building material that we've had around for a number of years. I mean, it is one of probably the core building material of any construction site that you see. It is an extremely reliable and proven product for construction. That coupled with rebar for tensile strength allows us to use concrete in a number of applications. The very high strength obviously is one of the key applications. However, if we don't protect that concrete, there are certain conditions that we can put that concrete in that can reduce the life of it. We're going to talk as we move forward about ways that we can protect that concrete against some of these things that may attack it. So, some of the ways that concrete can be attacked are through corrosion. That can be through microbial induced corrosion. It can be through, if you're in a chemical facility where you're storing an acid or a salt, or it may be, we can also have, incrustation. Concrete, it makes a good base for other biological media to attach. We can have spalling, we can have leakage, which could be caused by cracks or, from seismic activity or other poor placement of a pipeline. We can have leakage that is caused by root infiltration. And we can also have abrasion. So we want to address each one of those. Any of these can cause, high maintenance costs. They can cause environmental issues and pollution, and they can reduce the system performance. And over time, they can reduce the service life of the structure that's created by the concrete. So looking here is one example of corrosion, and this is an example of how microbial-induced corrosion works in a wastewater environment. So we have sediments in the wastewater that generate, under anaerobic conditions, generate hydrogen sulfide gas. That gas condenses on the upper structure of a pipe. It creates, the microbes there convert that hydrogen sulfide gas into sulfuric acid, which can eat away the pipe, ultimately expose the rebar, eat away the rebar, and cause a failure in the system. In addition to that, we also have chemical corrosion in containment facilities, which are containing acids and salts and other corrosive environments, and hydrolytic corrosion as well. Moving on to product features and how we can protect against this. There's two basic ways. There's different types of lining or protection that we can use. A lot of times we'll see a coating, an applied coating or applied lining, I should say. I refer to them almost always as coatings. A lot of other people will refer to them as linings, and that confuses me because I think of a liner such as a concrete protective liner when I think of a lining. But I'm going to call them coatings for that reason. So, if we put a coating in, typically our experience and the experience of our customers is that we're looking at in a normal average condition, a lifespan of 10 to 15 years. At that point, you're going to have to go back in and rehabilitate that structure by applying additional coating. Most of the coatings require a very clean, a very appropriate surface for the application of the coating. So in order to reapply more coating, a lot of times it is required that we do a lot of sandblasting or demolition of the existing structure to get down to a good surface to reapply. So there can be significant cost with rehabilitation or recoating these structures, and they can also cause serious downtime or interruptions of processes that we're using that structure for. Using a concrete protective liner, easily we're looking at least 25 plus years. When we design a facility, usually we're looking at a minimum of 25-year life. That's where we begin. We've got structures in place with concrete protective liners that have been, in service for over 25 years. We can pressure wash them, clean them off, and it looks brand new. One of the advantages of using a thermoplastic liner in conjunction with a concrete liner is that you get the best of both worlds, so to speak. We get the strength of concrete, which we talked about earlier, but we also get the elongation and the corrosion resistant properties of a thermoplastic. So in the event that a structure cracks, the concrete protective liner has the ability to stretch and bridge that crack and maintain containment. Thermoplastic is also very corrosion resistant. So it's resistant to most acids and salts and has a very wide temperature range, and there's a variety of resins that we can provide to meet almost every potential need. We have a very safe and fairly simple installation. The material has minimal maintenance cost. a very high impact resistance and shear resistance. It is very high from a chemical and abrasion resistance standpoint, and also has a very long service life, as we mentioned. Here's some of the production lines and how we make this material. We have production of this particular product in both Bad Hall, Austria, and also here in Georgetown, South Carolina, where I'm calling from. They're designed with the latest state-of-the-art technology. We design these machines, these extrusion lines in-house. They are state-of-the-art. We have a very qualified staff and quality control system to ensure that we have the highest quality components. We've been producing concrete protective liners since 1986, so for over 30 years. And for well over 25 years, we've been making it in its basic, the same design that you'll see in just a moment with the V-shaped anchors. From an abrasion resistance standpoint, we mentioned earlier, this is a chart showing various materials when exposed in the Darmstadler test. The Darmstadler test is a trough where we line the trough with a material, be it concrete or FRP or polyethylene or polypropylene, PVC. And there's a slurry or a solution placed in there with an abrasive slurry material. And then that trough is tipped on one end, causing the material to flow or slosh down to the other end, and then it's tipped the other way. So it's rotated back and forth and causing the material to transfer from one end of the trough to the other, back and forth. And in this graph, what we do is we measure along the y-axis the amount of material, or the wear of the material that is lost. So the thickness of the concrete protective liner, or the thickness of the concrete that is lost over a number of iterations where that material is sloshed back and forth. And you can see that both polyethylene and polypropylene perform extremely well in this, much better than concrete pipe alone. So the polyethylene is going to extend the life of a concrete structure from an abrasion standpoint, as well as a corrosion standpoint. If you hadn't seen it before, this is the basic design that AGRU uses in our concrete protective liner systems. We have these V-shaped anchors, and we have about 39 of them per square foot, translates to around 420 per square meter. We have a very high shear resistance for these studs. The anchors are integrally cast with the liner system. So when we extrude the sheet, the anchors are cast at the point of extrusion, when it comes out of the die, through a calendaring process. So it's not that the anchors are added later. So this integral process allows us to have a very high shear resistance, or very strong adhesion of these anchors to the host sheet, since they are integrally part of it. We have several different anchor types or stud types that have varying pullout resistance. And as I said, we've had this system in effect for 30 years. There's a couple of tests when we look at concrete protective liners. Most polyethylene or most polypropylene is going to perform the same in a tensile strength, as long as we're using high quality resins and we're not using recycled materials. AGRU uses very high quality first run virgin materials, and we believe that we know that results in higher quality products. But other than that, your polyethylene and the tensile strength in many cases is going to perform very similar. What most of the time people are looking at in a concrete protective liner is two things. They're looking at pullout resistance, and probably more important, back pressure resistance. So first off, I'm going to talk about pullout resistance, how we test for that. And then we're going to talk a little bit on back pressure resistance, and then a few more items. But, this is a back pressure test on how we would measure the strength of the liner, or the ability of the liner to stay cast into the concrete. Before we talk about either this test or the back pressure test, we need to qualify that all tests are not created equal. There are a number of factors that can affect this test, and can affect this test in some fairly drastic. One of those, which is certainly very important, is the strength of the concrete that is used. If I use a 10,000 psi concrete, then I'm going to get a much higher pullout or a much higher back pressure resistance than if I use a standard 3,000 psi concrete. So AGRU's opinion is that we should publish data based on the least common denominator. When we publish data, it is based on a 3,000 psi concrete. Other manufacturers of concrete protective liners may publish their pullout resistance or their back pressure strength based on 5,000 psi concrete. It's very important that when you look at these things that you make sure you are comparing apples to apples. If you look at the picture in the center of this slide, you can see that when the liner is pulled out of the concrete, it actually takes a lot of the concrete with it. So that's why concrete strength is very important, because usually it's not just the liner deforming and coming out, it's breaking up the concrete with it at the point of failure. In this case, we've got the concrete protective liner. We've cast that into a slab of concrete. We attach a force to that concrete protective liner, and we increase that force until the concrete protective liner pulls out of the concrete. So if we were to hang something from a liner, this would be an applicable test. If we were to have a vacuum that was created, this is somewhat of an applicable test. But more often than not, where we're concerned about is back pressure. In this slide, we'll show the three different anchor types. We have our type 560, which is standard Sure-Grip. Type 571 is a little taller anchor. That's a 19 millimeter anchor. In there we can see we get about 690, and the Ultra-Grip anchor system is 820. So we'll show those in a little more detail moving forward. This next test is the back pressure resistant test, and I'm going to explain why we believe this is probably a more important test than pull-out resistance. A lot of these structures are in pipes, in tunnels that are below potentially water table. Therefore, in the event that the concrete structure were to crack, we could have a back pressure that would develop behind the liner, pushing the liner out. And we think that is probably a situation that is more often than not encountered more often than the pull-out resistance. So we believe this is an important. In this application, or in this test, you can see that we cast the liner into a concrete slab, but we have ports through that slab where we can apply a liquid back pressure. And when we apply that liquid back pressure, we actually slowly increase that back pressure. If we were to rapidly increase the back pressure or rapidly increase the pull-out force, then we would see a higher number. So by slowly increasing that, you get a more accurate number and a more conservative number. In this case, you can see in the sample on the right that we've got a weld in the middle of our sample. We want to make sure that we're testing all possible situations, including what could be the weakest link in a weld. And we apply this back pressure, and in addition to applying it slowly, we apply it over a long period of time. So we usually do a 1,000-hour test with that back pressure to make sure that over time, the back pressure does not cause the liner or the anchor system to fail. Here's a graph that shows the three different stud types or anchor types. Type 560 was the original Sure-Grip design. Type 571 was a little higher anchor design. This can be very useful in areas where we are flowing grout in a hose lining process or in a floor lining process potentially. We get a little higher back pressure resistance, but ultimately the Ultra-Grip system is where we get our highest back pressure resistance. So all of the material made here in Georgetown, South Carolina is a relatively new machine. All of the material made here is with the Ultra-Grip anchor system, so we see our highest back pressure resistance. You can see that the anchors are, the bridge between the forks of the anchors has been raised, and also in the opposite direction, the anchors have been flared out slightly. And this is what gives us that additional pull-out and back pressure resistant strength. Go through this kind of quick, but if we look at the cost, the bright blue material on the far right is a 3 millimeter AGRU HDPE liner. When we compare it to other typical lining systems, it's not the most expensive, but it's not the cheapest either. However, when we move on and we look at the life expectancy of this, you know, we have the highest life expectancy. So even though we're not the most expensive, we provide the longest life. And what that results in is over the life expectancy of the facility, of the structure, we see a very cost-effective lining system. So moving forward, we talk about the supply range that AGRU offers for concrete protective liners. Primarily, you'll see high-density polyethylene. Polyethylene is the workhorse of the industry, both in the geomembrane and the concrete protective liner side. So we offer these four base resins, and within those, we offer a few different variations of each of those individually as well. AGRU has a range of thickness between 2 millimeters up to 12 millimeters in thickness. The vast majority of the time, we're between 2 millimeters and 5 millimeters in thickness is what we see. We offer this in a single and as well as double containment systems, a dual sealing system. We have a bionic surface, we have signal layers and anti-skid. I'm going to show you on the next slide. You can see a little better how that's set up or how those systems work. And we can do custom widths. So if your project is big enough, we have our standard products off the shelf. But if your project is big enough, we can specifically make a width that matches what you need. And we do different configurations as far as smooth edges, where we don't have anchors on one side or both sides, for wedge welding or for other installation techniques. And then lastly, we can put a polyester fabric back sheet on the top of it, on the face of the smooth face of it, for transition to other materials. The one thing to look at is the temperature limits. So with the various resins, this is more often, in many cases where we see the need to go to a different resin other than polyethylene. 60 degrees Celsius is about 140 degrees Fahrenheit. That is considered the operating temperature. So that's the temperature at which your media would be in there operating. Not a spike in temperature, but the constant overall operating temperature would be a maximum limit of 60 degrees Celsius, 140 degrees. For polypropylene, that number is 90 degrees Celsius. That's 194 degrees Fahrenheit. For PVDF, it's 120 degrees maximum, and that translates to about 240 degrees Fahrenheit. And finally, ECTFE is 140 degrees Celsius, which translates to 284 degrees Fahrenheit. We can use a variety of formworks, from monolithic formworks to climbing and slip formworks. This is just a couple of different ways that we can seam or weld the material together. And it shows which one of these materials. When we're dealing with polyethylene, we have the option of using all four methods. The second one, extrusion welding, is by far the most common. For more detailed work, you may use the top method, which is a hot gas or hot air fusion welding process. Because it's cast in concrete, and normally before it's welded, it's a lot of times difficult to hot wedge weld this material, but it is possible to wedge weld panels together and then cast them into concrete. And finally, there's butt fusion welding, and we'll see a lot of this particularly when we're making tubes for pipes, where we use a sheet butt welder, similar to the way that an HDPE pipe is welded together by butt welding. We can do the same with sheets. So we'll form the sheet into a tube and weld it with butt fusion. So that's more of a fabrication type system. Just to give you a little better idea, if you're not familiar with the welding processes for thermoplastics, on the top left, we see hot gas or hot air welding, which uses a bead of weld rod and hot air to seam two sheets together. Moving clockwise, we see extrusion welding, where we're also using a piece of weld rod, but we have an extrusion on that. We have two components on that extrusion gun. One is a hot air leister, which is heating up the parent materials, and the second component is an extruder, which is chewing up, grinding up, heating up that weld rod and extruding it out through a Teflon shoe. So it's a much higher production welding method than hot gas welding. And then finally, we see hot wedge welding on the bottom left, and we see the butt fusion welding on the bottom right. A few items that we offer to facilitate our installation. We offer the corners if we've got a rectangular or square containment facility, we can use these corners. More often than not, the other two are what we see use if we are lining a tank structure and we need a water stop. We can use the termination profile, which has a bit of a water stop there to in the event of overtopping of the liner system, that we won't get water back behind it. And then Probably the most common profile that we offer is the tear-off profile in the bottom right. It's also shown in the picture on the right. And what that is that's a profile that is used to join two sheets together. So the sheets, it's sort of an H profile where the two sheets are pulled into there tightly. This ensures that the gap or the distance between the two sheets to be welded is the same and is consistent. It also ensures that in the opposite plane that there is no fish mouthing between the sheets. When the material is cast, one of these, the face of the tear-off profile, just as it's described, can be torn off. And this profile is made out of an electroconductive polyethylene material. So the backside of the H profile, the curvy side, is left within the concrete. So when we weld our sheet together, because that piece that is back in the concrete behind the two liner, behind the weld, is electroconductive, we can spark test or holiday test back to that without the need for a copper wire. So here you see a precast pipe that has been lined with concrete protective liner. In this case, on the bottom right, you'll see that the tubes were formed up, probably using a butt welder. They can be slid over the inner formwork for the precast at the precast plant, and then the concrete is cast between the inner and outer formworks, and the Sure-Grip concrete protective liners integrally cast into the pipe. Very similar methodology for manholes and other precast structures as well. Here's a sewage treatment plant. Both will have cast in place and precast applications. Tanks, digesters, fermenters for farms and other facilities. This is a storage tank for purified water or potable water. Here are some tanks used for desalination plants for brine storage. This is actually a combination of concrete protective liners and geomembrane liners in this application. Secondary containment and floor linings. And then lastly, the last method is for tunnel systems. And we've done quite a few tunnels. This specifically is a project in Singapore. It was called the Deep Tunnel Sewer System. Pictures here, the majority of the tunnel was a bored tunnel. It was bored with a tunnel boring machine, a TBM. As you see in the bottom left picture, there were the ingress or egress. We did have some that were cast in place, cut and cover type tunnels. That concludes our presentation. And if there's anything we can do or help you with, we hope that you'll contact us.